Hello everybody, this is probably my last set of notes for the chemical equilibrium section. We'll move on to, I believe acids and bases is next. That's actually, I would say this and the kinetics chapter are the most intensive of all of them. That's my opinion, maybe you'll disagree. We're going to talk about, roughly on page 23 of the unworked out notes, we're going to talk about how making perturbations or small changes to the system will cause shifts in equilibrium. We've kind of talked about these ideas all along. I just want to introduce a term. I don't use this term much, but you will hear chemists say Chatellier's principle, and every time I say it a little differently. I've listened to 3 or 4 videos of this beforehand to try to hear how other people pronounce it, and they all said it a little different. So it's one of those type of terms that, you know, he's not around or she's not around anymore. I'm not sure who the person was actually. But this is a principle that I will explain from more of a physical chemistry vantage point that makes sense to me. It's how the system restores itself when a change is made to it. We're going to make these changes for now isothermally. That means at constant temperature. So the way I imagine equilibrium, I'm going to write down a reaction that we did earlier. We had H2 gas in a prior video plus I2 gas, the old gas phase, and equilibrium with 2HI, and that has an equilibrium constant at a certain temperature. I don't actually remember what it is, but K. And in this case, Kp and Kc are equal because we have a 2 here, right? And 1, 1. Our delta N of the gas phase species is 0. So if you go back to how we converted, there's an RT raised to the delta N linking together Kp and Kc. Anything raised to the 0 is going to be 1. So Kp, let's just say arbitrarily at a certain temperature, is around 50, right? So we have a value for it. That's the only thing. So we have a reaction coordinate. And the way you can think of a reaction coordinate over here, there's all HI, and over here, there's all H2 and I2. So it's a map, if you will, of how the reaction progresses along. It has some kind of scaling on it. So we'll say that, you know, this could be something like this. So you'll have free energy, not delta G, but G itself. So this is the Gibbs energy. Gibbs free energy. I'll put the technical name. I'm not worried about scaling. This is a cartoon. It's a conceptual cartoon. Isothermal process, meaning we have a certain temperature. So we'll have a map of G versus the reaction coordinate where the minimum is corresponding to K, the equilibrium constant. Whether it be Kc or Kp is a function of how we want to define. This will be in terms of the way we're doing the inputs in atmospheres. Here we're having the input in molarities. But the point is the minimum on this profile is where G goes to low point. Doesn't mean go to 0. G is where that along the coordinate, whatever the composition is of the HI relative to these species at that point. You know, we could get this thing in such a way we could extract from this numbers. The idea is to give you a sketch, but that's where K is. And notice, if you know calculus, if you took the derivative here, dg, d reaction coordinate would be equal to 0. And if you don't, it's going down here, G, it's going up here. So the point where it changes from going down to going up, delta G is 0. That's the equilibrium constant. That corresponds with delta S universe equals, you know, here also, we don't use it too much in experimental chemistry because it's hard to work with directly, but theoretically, delta S universe, the thermodynamic universe, not the cosmos, is equal to 0. So the big one we work with here is the equilibrium condition, delta G equals 0, and this is under constraints of constant T and P. I'm just going to put that down, focusing really on constant temperature, but there's a broader constraint here. We were worried about the details of that more in physical chem class, but the point is that over here, Q is greater than K on this side of the profile, and over here, Q is less than K. You could be over here. You can make a system over here, where in this case, let's write down, I don't know, we'll do it in kPs. kPs. So here, that would be the partial pressure of HI. Don't forget the squared. Kind of always do that myself. We have pressure of H2. It's to the first power. We don't have to write that in. I2. So in the case where, let's say we had, we changed the system, let's say it was sitting at equilibrium, and we suddenly added more H2 and or I2 relative to HI. We kept the HI fixed. We could shift the system over here to be where Q is less than K, and then the system would want to roll to the right. Roll to the right. It would shift right to products because it wants to reform more HI to restore equilibrium. So that's an example of, however you say this person's Le Chatelier's principle. And so on the other case, let's say we added, instead of, I'll just write it again, Kp equals PHI squared, PH2, PI2. Let's say we added more HI relative to H2 and I2. Let's say we keep them fixed and we add more HI. So in that case, the numerator is getting bigger, Kp, and you can make all the same arguments with Kc's with molar concentrations. Ends up over here somewhere. We've disturbed the system. And then so to restore equilibrium, that's the heart of Le Chatelier's principles, that isothermally, they should really put that in there, a lot of times leave that out, the system will try to restore equilibrium by shifting position. So in this case, it shifts left towards direction of reactants, I2 and H2, to let you restore the equilibrium condition. So when Q is greater than K, you shift to the left, and that's why I'm drawing the diagram with HI on that side and H2 and I2, just like my reactions, to be internally self-consistent, how at least in the Western world we define, we read from left to right generally. So at any rate, that's one of the ideas. Whether you call it that name or not, I really don't care. I understand the principle. Now, one of the things you can do is you could have this in a container. This reaction's going on in a container. You got H2, and you got a composition of these species floating around in a container in the gas phase, and you can compress it or expand it. So when you have, if it's behaving ideally, PV equals nRT, which means that we're doing this isothermally. So this is all a constant. At that point, this is a constant, right? So what we can say is that pressure and volume are inversely proportional. If you're isothermal, we're taking temperature just as a number here. R is a number, it's gas constant, and we're going to fix N. We have a certain composition of the system. And so the pressure is proportional to 1 over volume, right? And so in the case where you, for example, let's think about this, where in this particular case, we'll start out with this system here, when we compress it, nothing happens in terms of a shift towards away from equilibrium. We stay exactly where we are, because when you look at this, the pressures, you have a squared pressure here and a squared, these are all partial pressures, right? A squared partial pressure here and a squared partial pressure here. There's no net overall change in the ratio. On the other hand, if you have a gas phase reaction, let's take a different one. This is actually written in the notes, of 2 carbon monoxide gas plus O2 gas, and that's going in equilibrium with 2 CO2 gas. So we can write this, it's easier to think about this in terms of partial pressures. Kp is equal to P CO2 squared, P carbon monoxide squared, and PO2 to the first power. So total, we got something squared here and something cubed here. So what happens is, in this case, when you decrease the volume, you compress, you increase the partial pressures, And so that means this blows up more than the top. So the way you relieve that is, this new value Q, is you shift to the right to where you have less gas phase moles. There's a 2 to 3 ratio. There's 3 to 2, right? 3 on this side, 2 and 1, 3, 2 here. So you can see it's cubed, squared to the first, squared, total powers. So when you will shift when you increase the pressure to the side of less gas phase moles. And if you were to expand, in this case, you would shift to the side with more gas phase moles. You would shift, in this case, left. So that's another feature to think about. This is discussed on page 24. If we fix the volume of the system, it's fixed volume. We're doing this isothermally. We add some inert gas. Let's say we add argon to the system. Well, actually, I got the wrong chemical system here. I'm going to take the same one we have. So we'll have, let's just say we're just talking right now about the system with carbon monoxide. We got CO2, we got some O2, but let's say we add a lot of argon to it. Argon, that's an inert gas. It's non-reactive gas. And so we add an inert gas to it. We keep the volume of the system fixed. So what that means is the partial pressures don't change. There will be no change in the equilibrium constant. There's no shifting at all. So there's no change at all if you add an inert gas under constant volume, presumably isothermally. Now the case where, so let you get a good look at that. My cartoons here, all of this is written in or tabulated in the notes as well, but I think people like to hear me say it as well as read it. So these videos, I don't know. This is really my first time doing videos, as you probably can tell, and I don't know if people like this or not. I'm not sure. So this was all isothermal. Now, what happens when we change temperature is that we get a new profile. K shifts. This is when we change temperature. When we're not isothermal, we get new equilibrium constants. K is a function of T. K is not a function of concentrations. It goes back to where it was. It shifts back to, provided there's no new reaction chemistry or anything like that. But if you stay with the same type of chemical systems, you add more reactants or products to the system, you still have the same equilibrium constant at that temperature. Doesn't mean you're right there. It might take time to restore itself, but over time you'll get there. Now, I'm not going to explain Le Chatelier's principle. We derive the relationship where we have ln of K, the equilibrium constant, is equal to negative delta H naught over R, 1 over T, plus delta S naught over R. We derive that from an expression that linked together K and delta G naught, the standard state. These are standard state entropies in molar form, and this is a standard enthalpy for the process in molar form. So you're under standard conditions, which in terms of pressures is 1 atmosphere. Some sources will say 1 bar, they're very close. And in terms of concentrations, it will be, the book's using molarity, I'll use that definition. So at any rate, we know how this looks, right? If you have an exothermic reaction, we plot ln of K versus 1 over T. It goes up, and if you don't remember this, go back and watch that video again where I talked about this relationship. And so we have this is equilibrium constant again because we have a kind of a similar looking plot in kinetics. So here, this would be exothermic. Why do I know that? Because delta H, when it's exothermic, delta H itself is less than 0. And a negative of a negative gives you a positive, so you have a positive slope, right? The slope is negative delta H naught over R. That's the slope. So this is exothermic. Now look at this. This is 1 over T. Here's low T out here, and over here is high T. That's counterintuitive because we're plotting 1 over T. You may not be used to plotting 1 over something. So let's look at this. At high temperature, lower K relative to a lower temperature. Lower, ln of K, when K gets bigger, gets to be bigger. When K gets to be smaller, it's a positive value, not 0. It's a smaller K, right? ln of K is a smaller ln of K. So when ln of K is small, you're at your high temperature. When ln of K is large, over here, you're at a low temperature. So again, ln of K corresponds with K. High temperature, lower value of K. So K does change. In this exothermic case, how do we say it? K is decreasing as the temperature increases. So I am not going to try to rationalize this using Le Chatelier's principle. You're welcome to if you like, but I'm going to use equations we derived that are based on something more than trying to put a word salad to it like a lot of times the book does. I'd rather have a diagram explaining it. That to me makes more sense, but you're welcome to understand it any way you care to understand it. Let's take the case with endothermic. That's a reaction. It takes in heat from the surroundings. Now plot again 1 over T. Now in that case it goes down because again in our relationship ln of K I think it's called the Van Hoff form, something like that. Endothermic, delta H naught is greater than 0. Our interpretation of that in chemistry and physics is that you're taking in heat from the surroundings into the system. Exothermic, the system is liberating heat from itself into the surroundings. So here, a negative sign in front of a positive gives you negative, so the slope here is going down. And again, the high T region is counterintuitive to the left, and the low T is to the right, because we're plotting 1 over T, not T itself. Meaning, at high T, you got high K, because ln of K is high, and again, K gets big, ln of K gets big, and at low T, you've got a lower K. It changes with temperature. So, that's how I will explain it. You can read more in the note sets where it's more qualitative. I like it with a graph. And so that wraps up the big ideas of this chapter. This chapter will not be well understood without working a lot of problems. Work through the notes, rework the problems I've done on the board. If I made mistakes, let me know. I'll put a correction in. You always check the description. If I find I make a little typo on the board, I misspeak at a point, I put a note about it, and if you see me do something else of significance, don't go by you spelled wrong or something like that. I mean, my spelling's terrible. There'd be all discussion about my spelling. It's pretty bad. So this wraps up the discussion of equilibrium, but these ideas carry through to all subsequent chapters with the exception of nuclear, where we break form and we talk about something totally different. Really kind of outside the course, but we have to put it in somewhere. It's an important topic. It's really actually like one of my favorite sections, that and the kinetics I love, and I also love from last semester. For those of you who had me, if you hadn't, I'll just tell you what I love. I love the quantum chemistry section. I think that's great. I wish we could go into more detail, and I do in high level courses. So at any rate, on that note, we'll start acids and bases whenever I can make another video. So take care.